Good morning. So today we move on from Pythagoras, which is to do with the lengths of sides in right angle triangles, to trigonometry. And trigonometry is still to do with right angle triangles, and it involves angles as well. The word trigonometry comes from tri, three, gnome, which is Greek for angle, and measure, which is Greek, metra, which is Greek for measure. So three-angle measure. So that's where the name comes from. And so here is a right-angled triangle with a 30-degree angle as well. And we already know that the side opposite the right angle is going to be the longest side, and we call that the hypotenuse. So I'm just going to label that H. We are given two additional names for the other two sides with trigonometry. With Pythagoras, we just called them the two shorter sides. But with trigonometry, we have names for them. And it all depends on which other angle we're discussing. So in this case, I'm talking about this angle here. And the angle will always have one of its sides as the hypotenuse. The other side that makes up that angle we call the adjacent. So I'm going to write that here. Adjacent means next to, doesn't it? So it's adjacent to that angle. We've then got a third side. It's opposite the angle we're talking about. It's not involved in drawing the angle at all. So we call that the opposite side. Now, you could argue that O is a bit misleading because it could be confused with a zero. We've got to make sure it isn't. So we've now got ways of labelling the three sides of a right angle triangle. We've got the hypotenuse, which is always the longest side, the side opposite the right angle. Adjacent, which is the other side touching the angle we're talking about. And opposite, which is the side opposite the angle. And we always want to label them in that order. Identify the hypotenuse, then the adjacent, then the opposite. Now, for this exercise today, it really does need you to have a printout of these triangles. I've attached them, and I hope that's something you are able to do. If you have been able to print them out, then I'd like you very quickly now, while I pause the video, to label H, A and O on the two remaining triangles. Just be careful with this triangle. This is the angle we're talking about up here. Right, so with this one here, hypotenuse, opposite the right angle, longest side. This is the other side that draws that 30-degree angle, so that's the adjacent, and this is the opposite. And with this one here, that's the hypotenuse. Be careful this time. This is the other side that makes up the 30-degree angle, so that's adjacent and that's opposite. So what I'd like you to do now with each of the three triangles, and I'd like you to work in millimeters, is measure the length of the three sides in each case. Now, I attach this as an image, so we'll all have slightly different answers because it depends how your printer has scaled the image. And that's not a problem at all. In fact, that's sort of part of my design. I don't want us all to get the same answer. But what I'd like you to do is to set out your answers in a little table like this. So for the first triangle, how long is the hypotenuse? How long is the adjacent? How long is the opposite? Second triangle, third triangle. So I'm going to pause the video and get you to go away and do that for me. Now we all would have got slightly different answers because it depends how your printer scaled my image, which isn't a problem. But we're going to use the numbers we got, whatever numbers you got, to prove what the Greeks first realised when they developed trigonometry. See, they realised that these three triangles, although they are different, they're actually just enlargements of one another, aren't they? And so they realised that the relationship, therefore, between the lengths of the sides will be the same in each of these triangles, even though they're all different sizes. And so they realised that the multiplier linking hypotenuse and opposite would always be the same in a 30-degree right-angled triangle. The multiplier between these two sides, they'd always be in relationship. They realised that the multiplier between hypotenuse and adjacent would always be the same, and that between adjacent and opposite would always be the same. So let's test it for the first triangle. If I do work out the multiplier between hypotenuse and opposite, which you'll remember from ratio we do by doing after divided by before. So I'm going to do 58 divided by 115, and that gives me 0.50. I'll round to two decimal places. So that's, if I do this ratio between hypotenuse and adjacent, so that's after divided by before, that gives me 0.87 if I round to two decimal places. And if I do the multiplier between adjacent and opposite after divided by before, well, I don't need my calculator for that, do I? That's 0.58. And what you should find is that you get a very similar multiplier if you do the same three sums for triangle 2. I apologise for my sniffing today, hay fever season, so sorry about that. Let's do opposite divided by hypotenuse, 39 divided by 79, and that's 0.49, pretty much the same as I got with the first triangle. And if I do adjacent divided by hypotenuse, 70 divided by 79, I get 0.89, pretty much the same as I got with the first triangle. And if I do 39 divided by 70, I get 0.56, pretty much the same as I got with the first triangle. And I won't do the third one, but if you go on a test with the third one, you should find you get very similar results. For a 30-degree right-angled triangle, O divided by H is always about a half. A divided by H is always about 0.87. And O divided by A is always around 0.6. And the fact that we didn't get exactly the same with each of our triangles, well, that's just because I hadn't drawn them accurately, perhaps, or you didn't measure carefully enough, or I didn't measure carefully enough. But the fact of the matter is that if we had been exact, those sums would always give us the same answer, regardless of how big the 30-degree triangle is. And the Greeks realised something amazing. They said, well, actually, it doesn't just work for a 30-degree angle. For any right-angled triangle where you know the size of one of the other angles, you can predict the answer to those three sums. Opposite divided by hypotenuse, the multiplier that takes you from there to there. Adjacent divided by hypotenuse, the multiplier that takes you from there to there. Opposite divided by adjacent, the multiplier that links those two sides. You can predict it for any right-angled triangle and any other angle. And so they gave those three sums a name. The sine of an angle is the name they gave to the multiplier linking hypotenuse and opposite, so the O divided by the H side. Its full name is sine, but we always abbreviate it to sin, but we still say it as sine. The multiplier linking adjacent to hypotenuse, so that's A over H, is known as the cosine of the angle. We abbreviate that to cos, and the relationship between opposite and adjacent is called the tangent of the angle, which we always abbreviate to tan. And so if on my calculator I go to the sine button and do sine of 30 equals, I get a half, which is what I found when I was doing those measurements a moment ago. And if I do the cos of 30 degrees, this was the one that was about 0.8, so cos of 30 degrees yeah, 0.87. And then the last one, the tan of 30 degrees, 0.577. Well, yeah, I got 0.58 and 0.56. So the Greeks realised that it was predictable, and it wasn't just for 30 degrees. They could predict it for any size of the angle. And the value of the sine and the cos and the tan of any angle is stored in our calculator. And we can therefore use that to work out missing angles in right angled triangles. So here is a right angled triangle. There you go, there's your right angle. Here's an angle. I don't know this angle. I want to work out the size of the angle, but I've lost my protractor. Still got a ruler, so we're going to use trigonometry to work out the size of this angle. And I'm going to use sine, and sine is all about the relationship between O and H. So I'm going to firstly label up my sines. Remember the order? Hypotenuse first, then A, and then O. So hypotenuse is always the longest side, so that's the hypotenuse. The adjacent side is the other side that makes up the angle, and then the opposite side is the one opposite the angle. Now I'm using sine, so I'm only interested in the length of the hypotenuse, the length of the opposite and the length of the hypotenuse. So I'm just going to pause the video and measure those two as accurately as I can. So I got 104 and 88. Remember, I'm using those two because the question says use sine, and sine is the name given to the multiplier between O and H. Now, I want to know what the angle is, so I'm going to write out this rule. And then I'm going to fill in the numbers. O is 88, H is 104. And then I'm going to get my calculator to tell me what angle has this as its sine. We know that the sine of 30 degrees is a half, but I want to know what angle has 88 divided by 104 as its sine. And I'm going to show you on my big calculator, which is a bit like your scientific calculators, but also on my mobile phone calculator. Now, we've used the calculator already to work out the sine of an angle that we knew, but now I'm going to use the calculator to work out the size of the angle. So that's the reverse. So for that I'm going to use the shift sine function, and this will work on, I know my calculator's big and fancy, but it'll work on any scientific calculator. If you use shift or inverse and then sine, it should come up with sine to the -1. I'm then going to put brackets, and then I'm going to type in my sum, 88 over 104. You can either do 88 divided by 104, or you can use your fraction button. You'll get exactly the same answer, whichever way you do it. Okay, so I'm going to do 88 divided by 104. Then going to close those brackets. So what I'm asking here is, what angle has a multiplier of that linking its opposite and hypotenuse? And that's the answer, 57.7. So I'm going to round these to the nearest degree. 58 degrees. Okay, let's test it. I found my protractor. Let's see if that angle really is 58 degrees. Well, it's a bit hard for you to tell on the video, but there's 50, there's 60. Yeah, that's pretty good, isn't it? So I was told to use sine, so I worked out the length of the two sides, opposite and hypotenuse in that case. I then wrote out the rule and replaced it with the numbers. Then I used my calculator. Now, if you haven't got a scientific calculator, have no fear. If you rotate your calculator on your phone, so you get the scientific function, there's the sine, the cos, and the tan buttons. Now, I did shift sine on my calculator. I haven't got a shift button. I've got an inverse button, which is the same. So I do inverse, And look, it automatically changes the sign. So I do, there we go. And this one opens the brackets for me, which is helpful. So I'm going to do 88 divided by 104. And then I'm going to close the brackets. Actually, it's already given me the answer there, look. And there's the answer. That's the size of the angle. So you should be able to do that regardless of having a scientific calculator or not. Obviously, you can't use your phone in an exam, so scientific calculators are always going to be better. So 3 for you to try. These are on the second image I've attached. Again, you can't really do it if you can't print. But yeah, for the first one, I'd like you to work out the angle. I'd like you to use sine. So you're going to measure the opposite and hypotenuse side. For this one here, I'd like you to use cos. So that involves the adjacent and the hypotenuse side. And here I'd like you to use tan, which involves the opposite and the adjacent side. Now the 3 rules, you definitely need to write those down. The sine of an angle is opposite over hypotenuse. Sine is opposite over hypotenuse. Cos is adjacent over hypotenuse. Cos is adjacent over hypotenuse. Tan is opposite over adjacent. Tan is opposite over adjacent. So I find that little way of writing it out helps me remember, and that's where, if you've ever heard people talk about SOHCAHTOA, that's where it comes from, SOHCAHTOA. So I have posted a third image, which is my worked solutions to these. Obviously, when we're measuring, we're probably all going to be slightly different. You know, it might be a millimetre either way. But hopefully we'll get similar answers for the size of the angle. And if you've got a protractor, then you can check it by measuring it. Okay, let me know if you have any problems. Nothing to submit today, but on Friday we'll do some more practice of this, and I will get you to submit something. Take care.